have seen in previous lessons, once the measurement uncertainty has been correctly evaluated, a measurement result must be expressed in terms of a coverage interval built about the measured value with a given coverage probability. That is, with a given probability that the true and unknown value of the measurement falls within this interval. In other words, we expect that given this interval, for example the one you see here, the true value of the measurement, represented by the red dot in the figure, falls within the interval. This is what we expect, but what guarantees this? Or, if you prefer, what guarantees that the true value of the measurement does not fall outside the given interval, as you can see here? No matter how well we may have carried out the measurements and how much care we may have taken in evaluating uncertainty, we cannot be certain that we have considered all systematic effects and applied all the necessary corrections, or that we have not overlooked some influence quantity or some contribution to uncertainty. It therefore becomes necessary to have a measurement with a known value and known uncertainty so that by measuring it, we can check whether its value falls within the obtained interval or, if not, make the appropriate corrections. The known measurement is a measurement standard, and this operation is called calibration, which is defined as follows by the VIM in Article 2.39. Operation that, under specified conditions, in a first step establishes a relation between the quantity values with measurement uncertainties provided by measurement standards and corresponding indications with associated measurement uncertainties, and, in a second step, uses this information to establish a relation for obtaining a measurement result from an indication. Let's analyze this important definition in detail. The first point to note is that reference is made to specified conditions. This means that the result of a calibration is only valid under the conditions in which calibration was carried out. So, for example, at the same temperature, humidity, supply voltage of the instruments, and, in general, for the values that influence quantities had at the time of calibration. The second important point is that calibration takes place in two equally important steps. Let's begin by looking at the first step, that is, the one in which a relationship is established between the values of a quantity with their respective measurement uncertainties provided by measurement standards and the corresponding indications, including the associated measurement uncertainties. Let's suppose that the value of the quantity provided by the measurement standard is xs, with an expanded uncertainty capital U of xs obtained from the standard uncertainty small u of xs with a coverage factor equal to 2. Here you can see its graphical representation. Now, let's suppose that we have measured the same quantity with the instrument to be calibrated, and let's assume that the measured value is xm and that we have evaluated an expanded uncertainty capital U of xm obtained from the standard uncertainty small u of xm with a coverage factor equal to 2. Here you can see the graphical representation in the general case where the results provided by the instrument and the reference standard are not compatible. The relationship between the obtained values and the deviation delta between the two values is expressed mathematically by their difference as indicated by this equation. Obviously, since this is the difference between two measurement results, we must assess its uncertainty, which we can obtain from the uncertainties associated with xs and xm by applying the uncertainty propagation law. Since the instrument being calibrated and the measurement standard are different instruments, we can consider the two measurement results to be completely uncorrelated, and therefore the combined standard uncertainty associated with delta is given by the equation you see here. The first step of the calibration operation is complete, and the relationship found is reported in the calibration certificate issued by the laboratory carrying out the calibration. Therefore, this first step is typically carried out by the calibration laboratory. In cases where the instrument has one or more measurement ranges, such as with multimeters and scales, it is necessary to consider several points within each measurement range in order to characterize the entire range, as we will see in an upcoming lesson. It is now necessary to move on to the second step, using this information to establish a relationship that allows us to obtain a measurement result starting from the indication provided by the instrument under calibration. To do this, we need to consider that the instrument under calibration has given us the value xm, but it should have given us the value xs of the standard. Having evaluated the difference delta between these two values, we can correct the measured value by subtracting delta from it, as you can see in this equation. The standard uncertainty to be associated with the corrected value xc is always the uncertainty u of delta that we have already evaluated for delta, and which you see here again, because it combines the uncertainty evaluated for xm with the known uncertainty associated with the standard. From this equation, it is immediately clear that the calibration process results in an uncertainty that is always greater than that estimated for the instrument under calibration. It is therefore advisable to choose a standard with an uncertainty much lower than that estimated for the instrument being calibrated, so that its contribution, when combined quadratically with that of the instrument under calibration, is negligible. Let's now look at one last important aspect. In some cases, if the instrument allows it, it may be useful to adjust it in order to reduce the correction delta to be applied to the measured value. This operation is defined by the VIM in Article 3.11 as adjustment of the measuring system and should not be confused with calibration, since it does not involve any comparison with the standard. In fact, after carrying out an adjustment, it is generally necessary to proceed with the calibration in order to verify that the adjustment has produced the expected results. To summarize, we have seen that calibration is a necessary operation to ensure the accuracy of a measurement result. We have seen that it's an operation carried out under specified conditions and that it consists of two steps. The first step is generally carried out in the calibration laboratory, while the second one is the responsibility of the instrument user, who must use the information obtained from the first step to transform a simple indication into a measurement result. In the next video, we will see how to proceed in a practical case.